Yes, very good morning, everyone. In this video lecture, we'll be seeing about architectural patterns. But before to architectural patterns, we had discussed in last video lecture regarding introduction to patterns that there are three types of patterns, that is architectural pattern, design pattern, and idioms. When we speak about architectural pattern, it's a high level abstraction. You can imagine architectural pattern to be a very high level conceptual abstraction. In that you'll be when in that conceptual pattern you will be having subsystems, right, which we individually call it as a design patterns, and implementing of that particular design pattern in a specific language can be, we call it as an idiom, right. A idiom can be a small program or implementation. It is highly concentrating on implementation. Under that, the first type we will be studying is architectural pattern. So in this architectural pattern, there are mainly, we have grouped it into four categories. The first one is from mud to structure, distributed systems, interactive systems, and adaptable systems. Let us see the first category, from mud to structure. In this type from mud to structure, we are mainly studying about decomposition. Decomposition of the entire structure. How we are decomposing into entire structure. Uh, then the second type is of a distributed system. In distributed system, we'll be mainly studying the broker system. It means in this we are mainly concentrating if a sub process is distributed, or if a processes are distributed, then how we are studying the structure of that in this pattern. The next is about interactive system. In this, the well-known patterns are MVC, model view controller, and the presentation abstraction control pattern. Here, mainly structuring of human, we will be studying about human-computer interaction. The other thing is the adaptable systems. The adaptable systems, in this we'll be studying the microkernel and reflection. Here we'll be focusing more on the systems, how systems includes pattern that provide infrastructure for extensions. Right, mainly we will study how the infrastructure will be extended, or how it can be modifiability will be supported. So let us see from one by one. The first one is from mud to structure. So this is just a differentiation of the overall different patterns. You can see here in interactive systems there are MVC and PAC, adaptive, microkernel, and reflection. Under mud to structure, where it focuses more on decomposition of the entire architecture, the layers pattern, pipe and filter pattern, blackboard pattern. And under structural decomposition, there is other type, O, whole and part. And distributed system, there is a broker system. So under that first pattern category is from mud to structure. Under that, first we'll study about layers pattern. Then we'll see pipes and filter and blackboard pattern later. So what this layers pattern tells us. In this layer pattern, here the architecture pattern helps us to structure applications that can be decomposed into group of subtasks, in which each group of subtasks is at particular level of abstraction. See, in this layer pattern, we'll be mainly focusing on, there will be a how we are decomposing a complex system into different subparts, and all the subparts should be at the same level of complexity or same level of abstraction. It is not that one subpart is it's at a minute detailed implementation level, and the other is at a high abstraction level. No, all the levels, which how many levels which are layers which have been we are dividing, should be at the same level of abstraction. Let us study this layers pattern with help of a very common example which you have already studied in our computer networks. By this diagram, you can make it that this is the OSI 7-layer model where the layers have been divided from bottom to top is physical data link, network transportation, session, presentation, and application. So total 7 layers we have divided is been divided when compared to a composite task. Now let us imagine what is the benefit, or sorry, let us see what are the benefit of dividing this into so many layers, and are these layers are at the same level of abstraction. From this, you can see the layer 1, it has a specific role and responsibility. What is the role of layer 1? It transmits bit velocity, bit code, connection, etc. Right? The layer 2 detects, corrects errors. Again, layer 3, that is network layer, selects a router from sender to receiver. Likewise, all these layers, they have been given a specific task where that task is specifically performed that individual layer only. So you can just recollect from the last video of introduction to patterns that every pattern we will be studying with respect to three schema, or three structure, that is context, problem, and solution. So what I mean by context, context is nothing but the situation that gives rise to a problem, right? A context is a scenario which creates some problem. And next we'll see about problem, and the last part will be seeing about solution. Apart from these three main structures, we have additional things which we study regarding patterns. That can be it can be the structure of the pattern, it can be the dynamics, that is nothing but the runtime behavior of the pattern, it can be implementation of the pattern, it can be different variants of the pattern, its advantages as well as its liabilities. So for this layers pattern, the context is a large system that requires decomposition. So whenever we speak about such patterns, there is a large system, means there will be the complexity will be very high. So how what it is making us to do is we are thinking of decomposing the system and performing the task, subtask or subsystems in an entire whole architecture. So let us see about the problem description. After context, we will be looking at the problem description. In the problem description, so the problem description can be, there is a mix of high level and low level issues. So imagine that we are designing a complex system where some of the parts handle low level issues like hardware types, sensor input, reading bits from a file, or electronic signals from a wire. At the other end, there may be user visibility functionality such as interface of multi-user or higher level policies of different types. So there can be a mix of both high level and lower level issue, and there can be even high level as well as lower level operations, right? And high level tasks are usually complex, and we cannot be able to make a clean map of the lower level task. There can be even uh, when we develop a system, it might be desirable to make it portable between different platforms. The other thing we need to focus is about the forces, different forces we need to balance. See, whenever there is a change in any kind of a source code, it should not happen that I have to change, go on changing the entire architecture. So it should not ripple through the architecture. And the other thing is, I need to maintain an interfaces that is stable, so that if there is any alternative implementation or possibility of platform changes, then it should be smoothly carried out. There may be necessary to build other systems that have some even a lower level. Building when there is I have to build another system where they have got the same lower level issues. The next thing is there can be similar responsibilities should be grouped in the sense what I will be doing. I'll be doing similar responsibilities. It can be grouped into one of the particular layer so that every layer should be clearly specify what responsibilities it will be handled. At each component should be current. If suppose if the thing is that if one component implements various different issues, then the integrity of that component or that particular layer should be lost. I should be very keen in identifying the responsibilities of the individual layer, and it should be they should be coherent, and I should preserve the integrity among the component. And even it is there is no standard component for granularity. Whenever I speak about granularity, I will not initially will not be understanding whether the particular component will be coarse grained or fine grained. But when iterative decomposition will take place, we should have simple components. So when we go on decomposing iteratively, we will be having components with simple and specific response roles and responsibilities. The other thing which is very important is the work has to be divided among a team. So whenever I specify the different component and what are the roles and responsibilities of the various components, so the teams whichever have got the different components in the industry, the teams will be given with the different components, and they can start the work parallelly. Those teams can start the work uh, uh, parallelly. The other thing is structure the system as a series of layers. So this is kind of a generic solution that how we are going to build. So what we'll be doing, we'll structure the system as a series of number of layers. We'll start at the lower layer one, and we are going go on building the abstraction ladder by putting on layer J, layer J minus one, until we reach the one of the top. That is layer J, in the sense we'll be having an upper layer, layer J plus one, and a layer lower layer as a layer J minus one. So most of the services are provided by layer J, right? And from which are composed from layer J minus one. So layer J service may depend on another services of layer J. So you can imagine we are if there is a layer J here. If there is a layer j in this, there will be layer j plus 1, and there will be layer j minus 1. So each layer may be very simple or may have complex. Sometimes the individual layers will be very simple, or or it can be it can have a complex structure, especially the top level layers. Now we'll see the structure of an individual layer. One of the important aspect we have to look into here is about the CRC cards. So let us see what these CRC cards. Actually, these CRC cards are used as tools in an industry to build the various layers. So, or any can be any subcomponents or subsystems in an entire architecture. So let us understand what we mean by a CRC card. In this CRC card, where CRC stands for class, responsibility, and collaborators. So there will be three divisions where we will be defining the class. That is, in the sense that particular component, the responsibility that particular layer has got, and how it is collaborating with the other layers. Suppose if you consider that is a particular layer, layer J, in that the layer J has got responsibility that it provides services to layer J plus 1. That is, it is if this is layer J provides services to the layer J plus 1, but it delegates subtasks to level J minus 1. Let us see here. Here layer J provides services to J plus 1, right? And it delegates, means it delegates the task to J minus 1. Just see the relation between how layer J is sharing between the adjacent relations. and it is collaborating with layer j minus 1, not with j plus 1, but it is collaborating with layer j minus 1. Let us see different scenarios of the different scenarios of the usage. So in scenario one, what happens? The client it communicates to uh, that only the top layer n. It will not communicate to the other layers. The client will communicate to the only the top layer n. It will issue request to layer n. Layer n, what happens? It calls layer n minus 1 and the supporting subtasks. Again, layer n minus 1 may call to layer n minus 2 and so on till each it reaches to the bottommost layer. So the lowest layer level services are performed, and it will back again to the topmost layer until it reaches to layer n. Here layer j is actually the layer higher level of abstraction when compared to layer j minus 1. So this will be at higher level abstraction compared to this. So uh, the topmost layer at higher level of abstraction when compared to the lower layers. So this one can be the one of the scenario. Next is there is another scenario where there will be partial flow down. Sometimes a layer may be able to service the request without making the request to the lower down layer. So sometimes it may happen layer n or layer j plus 1 may get the task done only through layer j. We don't have to travel all through layer 1. Examples can be a caching layer where there is no need to maintain a state information when layer j can provide the services to layer j plus 1. It can be even that can also happen. The other thing is there is bottom of notification. The other thing we have to keep in mind is whenever there is some information needed from top layer to lower level, we either call it as a uh, or we call it as a request. But whenever there is a layer bottom layer wants some of the transformation or data transfer to upper layer, we call it as notification. Top down we call it as um, request, and bottom up we call it as notification. Here a device driver in layer 1 detects the input, and this transfers to the internal format and it notifies to layer 2. So it is notifying to this layer uh, 2. So like this the process continues up to the higher layer. The other scenario for is there will be only partial flow. Here the layer may be able to handle notification without forwarding it, because sometimes if there is a retransmission request, it can be handled by few of the layers. We don't have to go all through the various different layers. And the other is scenario 5. In this layers are typically known as the protocol stacks. Here one top layer issues a request which will be sent to the lower level, and other subsequent levels will perform the services, and until it will hit to layer 1 and data is transmitted, and if the reverse can happen. So see, whenever I see, you can imagine here the two scenarios of the OSI layers, one to this side, the other side, and you can from one application to other application how it will be happening from top down and the bottom up. You can imagine using two different PCs as well. Okay. Next, we'll see regarding the implementation, how we are going to implement this. The first step in implementation is define the abstraction criteria. So first, this is a very important thing. So first we have to define the abstraction criterion rather than defining how many layers are needed. So instead of defining how many layers are needed, first we have to define the different abstraction abstraction criteria needed for the particular application. So we can see that there will be conceptual distance from the platform. So whenever we imagine, think of the bottom layers, they will be more towards performing some kind of hardware task like reading the bits or transferring the bits. And as we go more on to higher levels, there will be a it will be highly abstracted. So and degree of customization of specific domains, and there may be even a mix of criteria. So, just like distance from hardware at lower levels. So we can imagine a OSR layer where physical layer performs some of the hardware kind of task, whereas the upper layer, the application layer, will be interacting with the user. So it's a high conceptual complexity. So the next step is determine the number of abstraction levels. So when we are clear with the abstraction criterion, the next is the level of how many levels of abstraction should be defined. See, there may be that each abstraction level corresponds to one layer. It can happen that there can be only one layer abstraction layer, but if suppose one abstraction only one layer of abstraction is there, then we are not taking actually much use of a layered approach, and all complexity will be grouped into a single individual layer. And there may be mapping from layers to levels to layers is not actually an obvious thing. And we should also think that we should not have too many layers so to impose unnecessary overhead, and there not be even two less layers. So what the best approach, we should have optimal layers. The other thing is, once the abstraction criterion is different and the level of abstraction is different, the next thing is we have to name layers and assign tasks to them. So when we are clear with abstraction criterion and we have got how many abstraction level these are, we have to start naming each layer. Suppose like in OSM model, I layer the bottom up layer as physical layer, right? And then the data link layer and top layer as application layer. So I go on naming them, and as you are knowing that each layer has got its own specific task. So the bottom layer has got its specific task of transmitting bits, and data link layer has got its specific task of detects and correcting the error, and application layer has got its provide specific task of communication activities. So it should be clearly named, and the task should be well defined. So it can take even a top-down approach as well as a bottom-up approach. So usually this top-down approach is followed, but to follow a bottom-up approach, it we require a lot of experience, which we get through a lot of working out on the application. The next is to specify the services. Here the layers must be strictly separated, means in the sense individual responsibilities should not be overlapping among all the layers. It should not happen that what the task which is being done by layer 1 is being again repeated by layer 2, it's been again repeated by layer 3. No, the task components should not be overlapped. So layer should be strictly separated, and it should not be spread over various layers. And we should also even see that uh, we should even also see that um, more services are performed in higher levels and fewer in lower levels. So as we go on to topmost level, they should perform more of the conceptual services. So this prevents developers from having to learn a large number of similar primitives. Means the most of the primitive tasks should be carried out only by the bottom of layers, and as we move on to top layers, most of the services they should the conceptual services they should provide, and also reduces change during implementation. Suppose if I include the implementation in the topmost layer, then it I'm making the a cluttery model here, or I'll ripple the code to different layers. So I should see to it that the primitive layers are at the bottom. So it should be just like a inverted pyramid. You can imagine an inverted pyramid, that how this topmost layers will be having different services. The next is The next is of the fifth step is refining the layer. So what we do, we should iterate from steps 1 to 4, so that we get the proper abstraction criterion, the different layers, the roles assigned to that layers. So if you get to that, then we will be able to reach some level of correct defining criteria and abstraction levels. So it should not happen all the once. So we should iterate to the process of steps 1 to 4, so that we are involved in refining the layering here. So it's usually not possible to define abstraction criteria without thinking of layers and services. And one more thing, we usually should not do that. We should not go to define components and services and then impose a layered structure. No, first we should think of the abstraction criterion, then the levels of abstraction, then the different components and services. So the natural solution to overcome this is to iterate to from steps 1 to 4. The sixth layer is implementation aspect is specify an interface for each layer. So this interfaces can be done through various approaches. Among this, we will see the three approaches is uh, black box approach, white box approach, and gray box approach. So how we are communicating between different layers, the communication can be achieved using black box, white box, or gray box. In black box approach, let us see in this case. See, in this black box approach, usually what happens is that this whenever I want to communicate from this, imagine this is layer 1 and this is layer 2. Whenever I want to communicate from layer 1 to layer 2, I will not communicate directly with the individual subcomponents. So there will be some middle component through which I am able to communicate with the other components. This approach, we call it as a black box approach, where this middle components acts as an interface from mode of communication from layer 1 to layer 2. The other approach is white box approach, where layer j plus 1 is the internal details of layer j. So it's like a kind of some much transparency compared to this black box approach, where the individual components can communicate. The other is gray box approach. In this, here there is a layer j plus 1 is aware of the fact that layer j consists of some of the number of components and addresses them separately, but does not see the internal working of the individual components. So what happens in this gray box approach, like each individual components are aware of the services of each other, but they interact with some other means of interface, but they don't know the internal details. So one of the best recommended approach is to go to the black box approach. It is considered as better than other approach because it's having a common mode of interface between the components. The seventh step is structure individual layers. So when an individual layer is complex, it should be broken down into well-defined different components. As you can imagine, that whenever I consider this box, I can call it as an entire an architectural design. But whenever I speak about the individual subsystems like subsystem 1, subsystem 2, subsystem 3, these subsystems can be called as a different design patterns. So these design patterns, they are having its own implementation approaches. I can combine the different implement design patterns to implement the entire architecture. The eighth step is to specify communication between layers. So in this type of when we want to specify communication, we use two different approaches. That is push model and pull model. So whenever there is some request being communicated from top model to the lower level, top layer to the lower level, we usually call it as a push. Or whenever there is some notification or callbacks, we usually call it as a pull model. So these are this push using push model or pull model. There can be communication between the layers. The ninth step is to decouple adjacent layers. Usually, there will be a coupling, top-down coupling and bottom-up coupling. In the top-down coupling, the upper layers actually know about what are the things going on the lower layers, but the lower layers are unaware of the identity of the user. Suppose you can imagine, whenever a client is communicating with the top layer N, the top layer is aware of which client is there, the identity of the client, but the lower layer, that is layer 1, is unaware of the client. So such kind of coupling we usually call it as a top-down coupling. But there can be even bottom-up coupling where we use callbacks to preserve the identity of the uh, clients. So we usually decouple by coding against. We usually have to code against the interfaces now rather than coding against the implementations. The 10th step is design error handling strategy. So error handling can be problematic in layered approach, as there are too many layers and every layer has got its own level of abstraction. So we should take care of all the error handling aspects and we should always try to handle the error at topmost layer rather than forwarding it to lower layers. So this is the overall weave of the 10 steps which we have seen for layer implementation. Next, we will see different variants of this layered approach. Variants in the sense, it is nothing but the specializations what we are giving to the approach. It is not that the entire architecture can be built only with only a single pattern. There can be a combination of different patterns. The subsystems can be implemented to different patterns. Whenever I speak about implementation, it is nothing but the EDM aspect I'm speaking. So the few of the specialization or variants we can give to this layered approach is we can have a relaxed layer approach. In this relaxed layer approach, each layer may use services of all layers below, not just adjacent layers. So what we seen in before, suppose there is a layer J and there is a layer J plus 1 above it and the layer J plus 1 below it. I said the layer J can only communicate with layer J plus 1 and layer J minus 1. But in relaxed layer system, it can happen that even layer J can communicate to the lower layer 1, right? Not just adjacent layer, it can communicate to all through the different layers. Some layers can be partially opaque. Actually it helps in gain in flexibility, but will be at a loss of losing maintenance. Usually it will be given in operating system or the framework where there is little maintenance and the high performance requirement is the most. The other known uses we will see is of the virtual machines. So we can very quickly recollect of the Java virtual machines, right? As the source code is background neutral and JVM is platform specific, it can be this can be one of the best known uses. Now we'll see some of the advantages of the layered system. So what happens, we can make use of layer, that is the layer use. So how we can make use of layers? See, if in the at the topmost layer, if the abstraction and interfaces are well defined, so those can be again reused. So we should always have well-defined interfaces and abstractions in the topmost layer. And even when the abstractions are well defined, they can even be made as libraries or frameworks. The other advantages here, the dependencies should be kept local to particular component so that it minimizes the ripple of the code, and it can even support portability from changing from one platform to the another platform. Some of the disadvantages, cascades of changing behavior. So if the behavior of some of the layers is changed, again we have to go through all the different aspects of the architecture, pass through different, we have to pass through the different layers. The other disadvantages can be, so system performance may suffer from layering overhead. If there are layering is too much, then again we have to go again through the different layers. So again, whenever and if you have too much of layers specified in a particular application, if when any there is a information transformation, then again we have to travel through all those layers. Even there is a information is very less, small kind of information, we have to traverse through all the layers. So we should not have too many layers or too less layers. We should see to it that in the abstraction criteria and abstraction levels are well defined, we have a optimal number of layers. Thank you.